Hi guys, this is a video on shared pointer. This is a smart pointer in the C++ language. Let's understand the problem that this solves. Remember that a smart pointer in general is a object that manages another dynamically allocated object according to RAII principles. That means a smart pointer is a class, and the class destructor is responsible for deleting an object to make sure that deletion happens perfectly. We've already covered the standard unique pointer in a previous video. Remember that a unique pointer is one kind of smart pointer. It holds a unique pointer to an object of type t, where t is a template parameter. Unique pointer is suitable when there's only one pointer to the object. So the operating assumption of unique pointer is that there's just this one pointer to an object, and that means that when the pointer is destroyed, the object needs to be destroyed as well every time. It's that simple. So the destructor of unique pointer always deletes the object that was pointed to. That actually handles most cases. The most common use of a dynamically allocated object is that it's a private data member in a class. When the class is destroyed, all of the private data members it owns should usually be destroyed as well. We also have another kind of smart pointer called shared pointer, and this handles a different use case when there are multiple pointers to the same object of a type T. So that's suitable when you have this situation where there definitely are multiple pointers to the same object, or there could be multiple pointers to the same object. This happens when you have something called an object graph. You have multiple objects that are all pointing at each other to represent some kind of piece of business logic, and we'll see an example of that shortly. The shared pointer deletes the object after the last of the pointers is destroyed. So if you start out with 4 pointers to the same object, and the first one gets destroyed, there's 3 left, the dynamic object remains. If there's 2 left, it remains. If there's 1 left, it remains. But when that last pointer into the object goes away, at that point it's safe to delete the object, and that's the moment when shared pointer deletes it. This handles pretty much all the remaining use cases of dynamic memory. There are a few other narrow use cases that are covered by other smart pointers and other usage patterns, but frankly, between unique pointer and shared pointer, that handles just about everything you commonly encounter in practice. In particular, shared pointer allows us to implement linked lists using smart pointers, which we're going to do soon. Here's a little example to show how this works. I've got 2 classes representing a shopping cart situation. I've got a product for sale at a store. It just has a name. In reality, this would be a more elaborate object with more data members like price and stuff. But to keep it simple, it's just a product with a name. And then I have a cart. This represents a shopper who has put an object in their cart. I think in practice, your cart would allow you to buy multiple items, but just to keep our example here focused on pointers, our cart only has one product in it at a time. So cart has a shared pointer to a product. And it needs to be a shared pointer because the way that shopping at stores work is that the store has a lot of products for sale and multiple people can buy the same product. It's not a unique pointer situation. If I put tuna fish in my cart, you can put tuna fish in your cart too. That's not a unique thing. So all of the carts need to share a common pointer to the same product item, defining something for sale. And there's an accessor for item. And the constructor takes a shared pointer to a product. Here's how you could use this. So I've got 2 cart objects, Alice and Bob. They're in unique pointers. I'm using the default constructor here, so Alice and Bob are null pointers at the moment. I use make unique on cart to make a new unique pointer to an Alice cart object. And the argument to the constructor, this here is calling the constructor of cart. So I need to create a product to give Alice. And I'm using make shared to create that product. It is just a product named Apple. And then Bob is initialized to be a unique pointer to a cart, and he is going to share Alice's item. So both Alice and Bob's cart objects are pointing at the same Apple product object. I reset Alice, which would free the Alice pointer. Importantly, Bob's pointer to the Apple product still survives. In my main here, I don't have any pointers to that Apple object directly, but still, that Bob object still has the shared pointer into that Apple object, and I can print it out, and it works. If I print out Bob's item's name, it prints out Bob has Apple as it should. Here's a little sketch of what's going on. Initially, Alice is declared, pointing at nothing. Bob is declared, pointing at null. Then I reassign Alice to point to Apple. So now Alice has one pointer into Apple. It's a shared pointer, but there's only one incoming pointer to Apple at the moment. Then we reassign Bob to point to Apple. So now we have Alice and Bob sharing this Apple object. The Alice.reset statement over here moves Alice to point back to null pointer. If we were using a raw pointer or a unique pointer at this point, Bob's pointer to Apple would be invalidated and Bob's Apple object would not work anymore. But since we're using a shared pointer, the Apple object survives because there's still one pointer to the Apple. It's not clear to delete yet. Then finally, we end the main function and the Alice constructor is destroyed. It's pointing at null, so nothing happens. And then the Bob pointer is destroyed. It moves back to null. That's the moment when there are no pointers pointing to Apple. The number of incoming pointers is 0. So at that moment, the shared pointer object deletes the Apple for us automatically. How does it do this? It does this using a technique called reference counting. The shared pointer objects together maintain an int counter for the number of pointers to the object. In the example before, Apple started out with 1 pointer coming in, then it got up to 2, then it went down to 1, and then down to 0 again, and then it got destroyed. So every time we have a shared pointer point at one of these managed objects, we increment the counter, and anytime a shared pointer is destroyed or moves somewhere else, we decrement the counter so that this int counter at all times really is the number of pointers pointing at the object. When it finally reaches 0, that means there are no incoming pointers. The object is unreachable, and at that moment, the object is deleted. This counting does add a tiny bit of time and space overhead because every object managed by a shared pointer needs this extra int. So there's the space for an int, 4 or 8 bytes. Not tremendous, but it is non-zero. Likewise, there's a little bit of extra time overhead because the computer has to increment these counts every time we move a pointer. That overhead doesn't exist with other kinds of pointers. Finally, some best practice for using smart pointers. For one thing, don't use raw asterisk pointers. They're error prone, and between references, unique pointers, and shared pointers, we can cover pretty much every use case for pointers in practical C++. Prefer to use unique pointer over shared pointer just because unique pointer has practically 0 overhead in it, and the shared pointer has a little bit of overhead for the reference counting. That said, if you do have a situation where you need to be sharing objects, such as an object graph or a linked list, go ahead and use shared pointers. That's what they're made for, and they work well. They're the right tool for that job.